Okay, we're ready to start yet? No. Okay, you late then, what happened to you? 很累，昨天睡到现在很累，睡太久了。Okay, so now you have been giving me draft, right? I give you feedback, right? So you have given me draft, okay? You have to give me soon, all right? Again. 来自队友的质疑。Okay, so you have been submitting draft by giving you feedback, right? So this is like a research already. Again, this is like research. Again, what you will expect in research. People give you feedback, okay, and then you do some changes, you answer people. Okay, so this is like what is research like? Okay, 这是人家怎么做研究。Okay，你告诉人家一些东西，然后人家再问你，然后你再给 feedback，然后就一个 discussion。Okay， so 很容易，I think you will ask one question, right? How people do research? How do you think what you do is correct? 有没有这样想过？为什么你觉得你讲的东西对？What's evaluation? Sure, 检查。So how to 检查 ？What's the criteria we use to 检查 to check? It's not because saying this is true, then this is true. Then you take it is true. No, you need to convince people. So how do you convince people? 你怎样说服别人相信你说的话？怎么样？Not enough. A lot of people evidence, and you need to argue. You need to argue by logic. Okay, 你需要逻辑 by logic. 不可以有逻辑漏洞。If you have a gap, people won't won't believe in you already. People will say, you always lie. I know you always lie. Okay. So you need to fill all the logic gap. Okay, no. So this is the same when you study my course here, especially. Okay, we stress on logic. Again, not just a solution. Okay, 我们不主张不于只是解题嘛，就是解答案。Okay, we solve the problem, but solve using method. Okay, not by solution. Okay, it's okay. So I hope you can jump out from your comfort zone. 跳出你的舒适圈，请跳出你的舒适圈 ，OK。Otherwise, you will feel very tired, very uncomfortable at this degree, because you still will meet more pure maths course in future. In second year, every sem you definitely have to take 2 pure maths. 你一定会拿到纯数的课，你一定要 prove， 你一定要有 logic。Okay, you have to have need logic. Sorry. Yeah, logic and then plus maybe some of your intuition. 所以招很 pure， 可以到 pure， 也算都 I mean apply 走到底都是 pure。Yeah, OK. So 什么是 pure 现在 ？Pure is 我们探讨那个真相，探讨它的这个追根究底，它的源头。OK 了。Please, I want you to get this out of this course. Otherwise, it's kind of wasted. So if you have problem, right? When I say something you think is wrong, you just point out, and then we can discuss. Okay. Please don't take everything what I say. I mean, you need to check what I say. What I mean. Okay. Okay. Does it make sense? Make sense or not? Okay. Please jump out from your comfort zone. OK， 从你的舒适圈跳出来，因为数学学生通常都是自我感觉良好的，真的自我感觉良好，非常良好。你知道人的眼睛是长在前面的，你有盲点，你看不到后面，你需要别人告诉你。OK 吗 ？OK，please please accept advice OK，otherwise you will be doomed in your life. Okay, because I'm not sure how long I will see you guys again, but if we miss this chance, then see each other again. Okay. Yeah. All right. So if you give me draft, I give you feedback. Make sure you know what I say, and then do the correction, and then we keep going forward and backward. Okay, until we reach some communion. Okay. All right. So there's a few concepts we want to revise again. Okay. So our first concept is about tangent plane. Tangent plane of surfaces. Or we will say level surface. Okay. So last time I mentioned already there are two ways to get this. Okay, there are two ways to get this. So first type of surface you will see is like right here. So first type of surface you will see is z equals to fx1. Okay. Second type of surface you will see is like capital Fx y z equals to 0. Okay. So example what? So example you can keep in mind, for example, the plane z equals to x plus y, or similarly z minus x minus y equals to 0. Okay, these are the examples you have. Okay. So you can try and find tangent plane at the point S0, Y0, and Z0. Okay. Try and find tangent plane at this point. So you are given a formula actually, right? So you are given a formula. So what's the formula of tangent plane? For example, for the case z equals to fxy. Okay. So the tangent plane here is tangent is z minus z0 equals to the fx partial derivative with respect to x, apply that s0 y0 x minus s0 plus fy at x0 y0 times y minus y0. Okay. Okay. How about for level surface? Okay, how about for level surface here? So level surface here even more general, right? Not just equals to 0, maybe equals to some k. Okay, any k. Any k in R. So in particular, you can take k equals to 0. So what's the tangent plane here? Okay, so what's the tangent plane here? What's the formula? Huh? Fx S0 Y0 Z0 times x minus S0 plus Fy S0 Y0 Z0 times y minus y0, and then plus fz of S0 Y0 Z0 times z minus Z0. Okay, equals 0. Okay, So what's the difference here? So the difference here is like this small f and a big f. Why? Because you start with small f and start with big f. Okay. And then why inside big f has 3 variables here? Because your big f need to take 3 variables input, right? Okay. But f here, how many input you take? Only 2. Okay. So are these two the same or not? Okay, which one imply which? Bf imply small f, right? Because for any z equals to fxy, I can write it in fxyz equals to k. Okay, how do I do that? How do I do that? How do I find bf here? Okay, so I can rewrite z equals to fxy into this form here. Okay, what does it mean by this capital xyz equals to k? Meaning what? Meaning all the variable x, y, z is on one side, equals to some real number. Okay, so I can rearrange. Okay, I can rearrange z equals to fxy to be z minus fxy equals to 0. So in this case here, what happened? We see that the capital fxyz in this case is just z minus fxy. Okay or not? So meaning what? Meaning what? Meaning I can apply the right-hand side theory to this capital fxyz, this specific one, z equal to fxy. Okay, so I can compute the tangent plane using this formula here. Okay, so let's try. So let capital fxyz equals to z equals minus fxy. Okay, so to get tangent plane, what do I need to compute? I need to compute partial derivative with respect to the 3 direction. Okay. Okay. So I need to compute what is fx, what is fy, what is f. So what is f little x here? How to differentiate this? So how you differentiate differentiate z minus fxy with respect to x. How do you differentiate this? Ivan, how do you differentiate this? Don't know. 分开 means what? Because the derivative is the differential operator is linear. Okay? So you want to 分开, you want to separate stuff, you need linearity. Okay, you need linearity here. Okay, so you can differentiate the individual term, right? Okay, so what do you get? How do you get? And what's the first term you get? 0. Why 0? 是因为 good, right? Good, very good. So z, there's no variable x here. So it is you treat it as a constant when you differentiate with respect to x. So you get 0. 0 minus what? 0 minus 1. Differentiate f with respect to s, you just get f s. What did you say? Okay, so it's just a partial derivative with respect to x. Okay, and this. Okay, so you get minus fx plus 1. Okay, how about fy? Similarly, you get minus fy. Okay, little fy. partial derivative of little f. Okay. How about fz? Yeah, 1. Okay. Because the second term here, there's no variable z. Okay. Okay, good. So we apply our formula here. Okay, what do we have for the tangent plane here? So fx at s0, y0, z0 is minus fx, okay, at x0, y0 times x minus s0 plus, what? Yeah, we make more spaces. Plus or minus fy s0, y0 times y minus y0, okay, and then substitute 1, you get z minus z0 equals to 0. Okay, so how about I make it into a line? Okay, so this is the answer. Okay, but we also have different answers just now. Okay, we have different answers just now. Let's bring this answer down. Copy. And then that paste. Are these two the same answer? Same, 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 right? Okay. So meaning what? Tangent plane for level surface is more general. Okay, than z equals to fx on the surface. Okay. Okay. So you can just remember the most general one, and then you can compute the easier. Okay. Okay, any question about this? No? Okay. Okay. Let's see. What should we do next? Okay. Okay. How about we look at this? Look at this. The level surface, the tangent space, tangent plane for the level surface here. Okay, let's look at this. Last time we didn't go into some examples, so let's so let us try to do some exercise. Okay, so now we want to look at a specific, okay, capital F X Y Z. Okay, let's look at the specific one. So take f x y z equals to x squared plus y squared z squared minus 1. Okay, do you know what this is? What's this? Can recall them? What's this surface? It's a sphere. Okay, it's a sphere. Okay, it's a sphere. Okay, so let's take a fine tangent plane at the point. Which point we want to see? Let's look at the point 0, 0, 1. Okay, so when I say tangent plane at this point, right? Does this point lies on my surface or not? Does this point lie on my surface? Yes or no? Is 0, 0, 1 satisfy the capital F equals 0? Yes or no? Yes. So you sub x equals 0, y equals to 0, z equals to 1, minus 1, is it 0? Yeah. Okay, 1 squared minus 1 is 0. So it is a point on this surface. So how do you draw this point out? Okay, how do you draw this point out? Yes, y here, you have z here, you have x here. Okay, so let's draw this hemisphere. We just need a hemisphere because we are looking at the northern hemisphere, 0, 0, 1. So on the top. Okay. Okay, so 0, 0, 1 maybe here. 0, 0, 1. Okay, 0, 0, 1. Okay, so last time what do we say? This plane here is what? Is all the place where the tangent vector of the path lies. All the path that pass through this point. So let me draw some path here. Okay. So okay, let's move these. How about move this point down a little bit? For me to easy to draw the path. Okay, let's move it down a little bit. Okay, I deform a little bit. So I look at all the path. Okay, that pass through this point here. Okay, I can take the tangent vector. Tangent vector of a path means what? Actually, it means the velocity of this path. Okay, yeah. So we can take this path and then we look at the tangent vector at this particular point here. Let's call it a t now. Okay. So let's do it quite concretely. Okay, let's do it concretely. So let's take a particular path. So for example, what path we can take? We just take the northern hemisphere arc. So for example, we take this particular path here. So it's a cos t 0 sine t. Okay, so what's this path here? This is a, what is this? This is a circle actually. Cos squared plus sine squared is 1. Okay, so what's this path here? So this is the circle here. Okay, you have a circle path, circular path, and then you take the tangent. So what's this tangent here? So this tangent here is minus sine t 0 cos t. Okay, but we want to look at the point where it is 0, 0, 1. So when does this path reach 0, 0, 1? When does this path reach 0, 0, 1? When t is equals to, t is equals to what? Pi over 2. Okay, so at t equals to pi over 2, r of pi over 2 is 0, 0, 1. Okay, so we want to look at this timing. I want to look at this timing. How is the tangent vector looks like? So how's the tangent vector looks like? So if you see from the picture, right, how do you guess? Can you guess what's this tangent vector here? Cannot. Cannot. So if you have a circle path, you go to the top part already. So what's the tangent line? It's horizontal. Okay, so we need to check whether this is horizontal or not. So r prime pi over 2 is 1. This one, 0, 0. Okay, so meaning you are tangent vector pointing minus 1. Okay, no change in y or z. Okay. Okay. Why this direction? Because your path is going anti-clockwise. Okay, so that's why your velocity is in this direction. If you go clockwise, then the tangent vector will swap. Okay, so depend on the orientation, the direction you move. Okay, so this is minus 0, 0, 1. Okay, and then we say that the tangent plane is all the tangent vector of all paths that passing through this particular point here. Okay, we look at all the tangent vector. Okay, so what is the normal vector to this tangent vector here? What's the normal vector? Remember how we derived the normal vector last time? How we derive it? So last time we start with a random path. Okay, so okay, this definition I need to remind or tell you. Last time I didn't tell you closely. So a tangent plane of a surface at S naught, Y naught, Z naught is the set of, okay, it's a set. It's a set of all, it's a set of all tangent vectors. Okay, it's a set of all tangent vectors of path on the surface passing through S naught, Y naught, Z naught. Okay, all of them. A plane is all the vector. It's all the vector inside. So if you look at a plane, right? Okay, what's the element in this plane? It's a point. Okay, but if you pick any point on this plane, right, all the point will form a vector with this point. Okay, so it becomes a set of vectors. Does it make sense or not? Okay, so you could imagine, you could ask, how I get maybe longer vector? How should I get all the long vector? Infinitely many long vectors. How do I get them? This depends on your path. So how fast you move in your path. Okay, how you increase your velocity? You need to do parametrization on your path. Have you guys did like arc length parametrization before? No. Reparametrization? No. No. Okay, maybe we'll see it later. Okay. I think you should have done it, but you forgot what you do. Yeah. Because you maybe don't know what you're doing. Okay. So for the same curve, we can parameterize this variable here to change the speed. Okay. To change the speed. Okay. Then we can get longer and longer vector or shorter vector. So we can get all the scaling just by reparameterize. We say reparameterize this variable here by changing the variable, scale the variable in more precisely. Okay, we can scale the variable. Does it make sense? Make sense or not? For example, okay, let's just give you an example. For example, we can write this as cos t/2 0 sine t/2. Okay, we can do this. Then what's the time you reach? For example, 0, 0, 1. What's the time? The time become pi. So meaning you take longer time to reach that point. Just now I only take pi/2. Now you need to take pi. Okay or not? So just by scaling the variable, okay, changing the variable, you can change your speed. Make sense? Okay. Okay. So last time how we derived this tangent plane here. So we consider a curve. Okay, so we always start with a curve. So this definition says what? Tangent plane depend on the tangent vector of path. So you need to take path first. Okay, you need to take path first. And then you look at the tangent vector. Okay, so tangent vector, you need to differentiate it. So how to differentiate this vector function here? You differentiate at every point. This is the definition. Okay. All right. And then, so how do I find normal vector to this vector? What's the natural way to see the normal vector? The hint is the implicit function theorem. The hint is implicit function theorem. So where do I put these path in? What equation can fit this curve? This curve lives on where? Of course, live on R3. More specifically, where am I working on? The path is on what? The surface. So meaning this path will satisfy the surface equation. Okay, I put it in. For all time I am on the surface. For any time, okay, I am on the surface. Okay, no. Anytime I'm on the surface. Okay. And then what can I do? I can differentiate this function. Okay. So if I differentiate this function, how to do? This, how many variable define f? 3, x, y, and z. But x, y, z are in turn defined by just t. Okay. So I want to do differentiation of f with respect to t. Okay. How does f change with t? So what do I get? So there are 3 paths here. Okay. So I need to add out the path. And then these edges are made up by the partial derivative. And then when you go down the path, you need to take the product of partial derivative. Okay. So I get del f del x dx dt plus del f del y dy dt plus del f del z dz dt. Okay. So you see this, they are product, okay, of partial derivative, and then sum of them. So this is like what? This is like a dot product. Okay, dot product of 2 vectors. So what kind of 2 vectors I can get here? So I can collect the del f del x to be the nebula f. Okay, the gradient of my function surface. Okay, the gradient. Right. Okay. How about dx, dy, dt? What are these? What are these? What are these? What are these? Where are these from? This is the tangent vector of R. Okay, these are tangent vector. So we get the result df dot r prime dt equals to 0. So you have dot product equals 0 meaning what? The angle is 90 degrees to each other. So they are normal to each other. Okay. So this del f becomes your normal vector of your plane. Okay. So del f nebula f is the normal vector of the tangent. Okay, so let's try this. Let's try this calculation here, right? Okay, so how do we do this calculation here? What is our nebula f? Let's compute our nebula f here. So let's write. Okay, so we have f capital F x y z here. So let's compute what is nebula f. So what is nebula f? Let me ask Sydney, what is nebula f in this case? Our big F is x squared plus y squared plus z squared equals to 1. What is nebula f here? So what do you get when you partial differentiate with respect to x? 2x, good. How about differentiate with respect to y? 2y and then 2z, good. Okay. So at the point 0, 0, 1, what does this nebula f become? What happened at the point 0, 0, 1? Dixon, what happened? What happened if I sub x equals to 0, y equals to 0, z equals to 1? It's just 0, 0, 2. Okay, at the point 0, 0, 1. It's just 0, 0, 2. What is 0, 0, 2? It is 2 in the z direction. So you have a normal vector going up. 0, 0, 2. So you can see that these two are actually really orthogonal to each other because the other one is minus 0, 0. Okay. Does it make sense? One is minus 0, 0, one is 0, 0, 2 at the point 0, 0, 1. Okay. Can see the picture or not? Can picture it using this example here. Can or not? Can you guys see this is actually perpendicular to each other? Right? Okay. So whenever we talk about a theory, a theorem, it must have some concrete example to see the theorem. Okay. If not, you can ask for the example. Okay. Okay. So whenever the mathematician or mathematics talk about a theorem, they have a concrete example. Okay. There's a concrete example. Yeah. Question, yeah, change it. What question? No, one.
When should we normalize the bank?
We done it when we try to find the directional derivative. Yeah. So what do you mean? Third product. Yeah. I mean, there's like I mean, this is just some calculation, right? Okay, but what we did before, yeah, is the what you trying to relate is this thing here, I guess. So let me turn it to that page. Just okay. You trying to relate to this definition. This definition, yeah. Okay, maybe this is not quite clear yet. So this definition or theorem. You mean why this U will have a unique vector? Because this formula can be realized as some dot product, yeah, forever. Yeah, so why we impose unit vector here? Why? I mean, I thought about this before actually. Yeah, why? Because on this, because about this. Because about this. Let's say if I don't take unique vector here, this U here, what will happen? The left-hand side is the directional derivative. It's the slope of my surface. So this slope here will become a product of the length of my gradient and the length of unit vector, or I mean the direction vector. Right? So means what? Meaning what? Meaning what? If I change the length of my direction vector, then the slope will change. You get what I mean? Even though you are in the same direction, you have a different length, you will affect this number here. You get what I mean or not? Let's say if I put 2u here, then what I get is 2 times the directional derivative you get before. You get what I mean? But I'm still in the same direction. So which number you want to take? You get what I mean? I think you cannot imagine what I said. Okay. Let me see how to say about this. Let me think how to say about this. So I take two surface. Okay, I take two surface. I intersect. Okay, I intersect. And then I get out the line. Okay. So this is the direction I'm looking at, for example, Z and X direction. Okay, X direction I want to look at. And then I look at this point here. I get this tangent line. Okay. Does this slope change if I look at x or 2x or 3x or 4x or not? Does it change? Will it change? Will it change? Will it change or not? If I this x is the direction I look at, right? If I change this vector x become 2x, 3x, 4x, does this slope change or not? Huh? No, no, right? But this formula here is very dependent on the length of direction vector and the gradient. You see, compute this directional derivative. It is dependent on the length of your direction vector. So if you change the length of your direction vector without changing the direction, you still change your slope. Okay or not? But what? By only one slope with one direction, right? You cannot keep changing your slope. Does it make sense? Does it make sense? Huh? Roughly 10. Okay. So we just make this directional vector just slope solely depend on my gradient of f. Make sense? Otherwise, the direction will alter your result. Okay or not? Okay or not? And if you have problem, you just keep asking because how to say, we need to maintain an effective communication here. Okay, otherwise you won't learn. And I don't know what I say is correct. Okay, so we need to maintain an effective communication. So you ask, I answer, I ask, you answer. OK 了吗？有效沟通，可以吗？来，让步。OK OK OK， yeah， 有效 ，yeah， 有效。OK OK 了吗 ？OK 啊。Any question? No. 151 already. We could take a break. Okay. Yeah. If no question, we could take a break. Yeah. Yu Yuan, have you seen your midterm yet? Okay, we take a break until 20. You can get your midterm. And Roshan and Yu Yuan, after you see your midterm, right, you can take a picture of it. You need to return the physical copy. The answer is on Moodle. You can check your Moodle. 啊，发给我。不喜欢，我现在只写到 post 完了，不要下一个 post。为什么？这里是 auto 的，然后这里直接 direct。不一样，原来是这样，这个是你直接发给我，然后再。大概就是手机的了，应该是 intro 写完之后就后面写什么？下面 history。对，他的 background，他怎么发的？找不到呀。好，那个 Wikipedia 这个我开过了，你开过了？对，你看过了。OK，好，你的那个信息要拿回去的。找啊，大概就是他的 history 对吧？对啊，他怎么来？为什么人家对他有兴趣？然后跟你没有太大的 OK。我知道是概念的。因为你就直接介绍它 as a theorem，and then 你就 prove 那个 theorem。 对，没有了。
会在抓查照片，需要照片，需要
不一定啊，不一定。但是如果你觉得有什么照片比较可以讲，
不一定。你上次讲过吗？西方老师，
我的照片，对不起。OK。
你看讲到这个东西啊，
就是
我画的图，因为它是这个点是应该是从这个点位移过来这边嘛，就这边这个点它是往上2个还是到002的位置？
往上2个，给我想想，其实是往上2个，对，
是从这个地方的往上2个
对，因为
斜跨弧，
因为
我就怎么？
对，因为是这样 ，OK， 很好，你刚才应该要问这个问题，因为我们一开始我们就是 find tangent plane on 这个点，所以意思说我们把这个点当成000，
我就把它当成原点，然后来进行一个位移这样子啊。
对，你刚才其实问一下比较好，我觉得应该有，
因为我看到那边写002，
对，
因为如果是
对，因为你要知道的一件事情就是这个002的这个东西，这个 vector 啊，我们重点是看这个 vector 的，这 vector 移来移去都是这样，但是就是像你讲的啦 ，translation，把这个001当做是 origin，
对方跨弧，
对，我知道你讲什么，
应该是放这个，或者是你放错放0，
应该都错了，其实放什么都错，就是说，就是说它是一个移调的，如果要最正确，我就要放003。
我刚才看你放002奇怪，因为我看你这个应该是从上面位移，可是它下面如果你放02是从原点。
对，OK，这样谢谢。
这个欧力放这些，
你给我想想，哦，我知道了，因为如果你放0下去这边的话，这个东西会消失，但是你放0下去这边的话，这个东西就 undefined。
但是I mean 这个 equation
啊，
等于 x 不等于0的时候，
对，
这样子的话，这个也只能是什么？
我觉得他应该是，如果他没有来回，除非像你讲的，我 impose delta s 不等于0，这样我就可以来回了。如果这个 in general 来说的话，delta s 可以等于0，可以的。in general 来说，如果你说我delta s 只考虑不等于0，这样我就可以来回。
Yes，这个对你讲那个 be careful，be careful 什么？那个就是当 G 不能是一个公式，然后我不是很明白什么叫做我只是在看 second， 那时候你讲当 G 不能是一个公式，
你写的不一样，我看不出那个 signal。你那个书还在吗？
那书
你好像跟他写的不太一样，看不太出那是不一样。你好像你没有那个 change of variable。
之前你讲这个是那个 in numbers，这个好像不是吗？
不是，它只 prove 那个 least upper bound 的 property。你那个 axiom 为什么会对？是因为这个 lemma。
这个 lemma 是讲，它就是类似，就是那个 least upper bound property 是 equivalent to 这个 if for every choice，然后 exist 什么，但是他没有讲那个 number 是吗？是用，它就是讲就是它有另外一个 equivalent 的，就是好像 least upper bound 的那 property equivalent to 这个 it and only。
对啊，这个意思是说，我可以找到 就是说，它这个意思是说，我有一个 upper bound for 这个 set 在这个 R 里面，这个 set 是任意的 set 在这个 R 里面，所以什么non 什么 set 都可以咯，也没有说难分别。所以它如果它是一个 upper bound 在这边，你要讲找它的 supremum，你就要修这个。
对，但是这个东西我觉得应该不用放进那 completeness 里面。但是我找到另外一个啊，它是讲，对，这里就是有说它的，
所以你 define 了什么是 completeness？define 了没有？
有
所以呢，什么是 completeness？
completeness 它有我忘记它那具体的 statement 啊，不过有在另外一本书里面，就那个不太重要啊，因为
重要，因为不然你不能要说。
因为我已经是知道了，我已经知道需要立什么条件，
你知道，但是我不知道你知不知道，所以你要告诉我你知道的东西。
OK， 这样的话我先拿回去。The essence of completeness， 然后好像
你要 prove 这个。
对，要 prove real number 是satisfied 的嘛，然后要放些什么 bound above 啊什么的，它那些 definition 啊，
没有错。
然后不过呢，要到 prove 那个 real number 是 complete 的时候，它需要那个 construction 是 ranking card 的。
如果需要你就要 introduce。这样它有用的话，它应该要有 introduce。
因为它另外一个它这本书
没有，我说他刚才那本，
这本
他如果这样写，他应该前面
有，
所以他就是这样咯。所以你要做的事情跟他一样。你有用到你就要。
我是 introduce 从这本书里面有什么这样，然后我不需要好像是 state 出来的，是不是？
什么叫 state？
就是它的，因为它有 real number 有3个 assume 是关于 order field 的，然后第4个就是 completeness。
有用到的东西你都要写出来。
有用到
有用到的东西你都要 report 出来。
要怎样讲呢
proof 那些。
我不需要好像是
proof 那些。
或者是什么啊？但是就是 completeness 那部分我需要部分
啊，对，其他的如果他们需要 proof， 你可以 assume 知道了，但是你要 state 出来，然后你说可能refer 这边可能 proof。
还有就是我的就是 reference， 你需不需要讲是 reference 从什么讲的？
如果能的话很好，就是那本书逗号 chapter 几。
必须要到第几面呢？
也可以的，其实有人做到这样，有人做到这样，可以做到那样。可是要开课了，等下再讨论。OK， 等下再讨论呢。好了。Okay, good. Just now, Ivan, right? Ivan point out a very good point here. Okay, so you see, I draw this 0, 0, 1. Sorry, let me go back. Okay, so Ivan point out a very good point here. So just now I draw here negative 0, 0, 1, but 0, 0, 1 on the top of 0, 0, 1. Is it something wrong here? Minus 0, 0, 1 should be lying on the origin because the z value is 0. Okay. So why I draw here? Why I draw at the starting from this point 0, 0, 1? Why did I draw this? Why did I draw like this? Why did I draw like this? Because I'm looking at the point 0, 0, 1. Okay, so more accurately, what should I do? I actually should add 1. I should add the point back. Okay, I should add the point back. Does it make sense? Make sense or not? Just now we have what line? What vector? So just now we have actually 0, minus 1, 0, 0, 1 is here. But we want this tangent vector and normal vector start from 0, 0, 1. So we somehow translate the vector. Does it make sense or not? So for example, you should think about this idea. Okay, you should think about this idea. So let me draw this picture here. Y, Z. Okay, X, Y, Z. So let's draw one vector here. Okay, what's this vector? 0. So let's put 1, 1, 1, 0. Okay. So this vector here, right? I can just translate it everywhere. It's the same vector, actually. What do you mean by same vector? It has the same length and same direction. Okay. But once I fix it at one places, then I need to do the translation. Okay, this is what I do just now. Okay, I need to translate my tangent vector to the right place. So I need to translate it. Okay. Just now, the coordinate I write here minus 1, 0, 0 and 0, 0, 2 is not translated yet. Does it make sense? Yeah, I need to translate it. Translate to the point that I am interested in. Okay, no? Does it make sense? Make sense or not? 为什么要 translate? 为什么要 translate? So what you computed is just a vector like this just now. It's just a vector like this. This vector start from 0, 0, 0. Okay. So just now, our vector should start from 0, 0, 1. Okay, we changed our origin already. Does it make sense? Does it make sense? Why not? Tell me why not make sense? I don't know why it doesn't make sense. 方向是一样的。方向都是一样的 everything. How should I say? Hey, correct. Wait. So, Ivan, do you know what is this vector? This vector is actually special vector already. So how should we talk about that vector? So I think we cannot. Huh? Yeah. This vector is a different vector. This vector is a different vector if I just shift like that. So how should I write that vector out then? Minus 1. Okay, so let's try this. So just now if I say okay. So I think do a stupid thing already. Let's see. So if I say like this, this is not minus 1, 1, 1. Right? Minus 1, 1, 1 should be something like this. This one. So this red color here is not the green part that we want. So what is that? We talk about this point then. Let's see. How should we talk about this green vector here? So the question is this green vector 1, 1, 0 is definitely not. Actually, it is yes, right? Okay. So this point here is 1, 1, 1. Okay. And then this point here is 0, 1, 1. It's still the same. It's still the same actually. Still the same, right? So this vector here is you take 1, 1, 1 minus 0, 0, 1. It is still 1, 1, 0. Yeah, it's still the same, Ivan, actually. Ivan is still the same. It is the same. Yeah. Because exactly what I said just now, you move this vector around, it's the same. If you don't change the magnitude of length or the direction, it's still the same. Because if you just shift this vector to 1, 1, 1 here, this become a different vector. Okay. Yeah, actually it's still the same. Still the same. Yeah. But you cannot see that vector as how to say as point. Yeah, it's not a point anymore.
You can
do that. Yeah, you can do that. Yeah, you can do that. You can do that. You can do that. Uh-huh. Parallelogram, right? And then you got A and B, and then okay, okay. I mean, so yeah, sure. So you mean this? You see this vector as this diagonal? Yeah. I think yeah. Okay, yeah. Ivan doesn't change the vector. Okay, doesn't change the vector. Yeah, I cannot just shift it. I think one is definitely true. Translation. If you think that yeah. Okay. Okay. Yeah. Okay. Good. Okay. Yeah, we want to motivate the this theorem again. Which theorem? The upstream value theorem that we left last time. Right. So recall what is the extreme value theorem? Okay, so if f is continuous on closed and bounded set D, okay, then f attains an absolute maximum value and an absolute minimum value. Okay, so what's this? So you should think of it as the generalization from the calculus one you have. Generalization from, do you have a name? Upstream, also called an upstream value theorem, right? So one variable upstream value theorem. Okay. So recall what have you done before? Okay. So what do you have in one variable? So if you fix one closed interval, okay, if you fix one closed interval, and then you have some continuous function here, you will definitely find the highest point and the lowest point. Okay. So the highest point or the lowest point will live where? Either it is inside within the interval or it is at the boundary point. Okay or not? Okay. So this is what you have learned before. Is this what you have? You want to check maximum point, minimum point in the middle of the interval, or you check the boundary. Which one is the greater? Okay. So similarly for two variable case. Okay. So for two variable case, you consider closed and bounded here. Okay. So we need to talk about what is closed and bounded. Last time we only mentioned about closed. Okay. But we haven't really talked about bounded yet. Okay. So what is close? You guys still remember what's the definition of close? Sorry? Sure. So let's get one definition first. So I say that a set C is closed. Okay. If closed in R2, if there's some open set S such that C equals to R/S. Right? This is what we discussed last time. Okay, I can write it as a complement of an open set. Then you are close. Okay, so meaning I need to tell you what is open. You still remember what is an open set is? How is a set open? How's a set open? A set is open if what? If for every point there's this open disk that lie inside the set. Okay, so you need to have a picture here. So what is open? So you have a set. Okay, you have a set. So you have a set. Okay, and then you have a point. Okay, you can always find an open ball inside your set if the set is open. Okay, okay or not? Okay. If you consider this point here, right? Can you find a ball such that it is lying inside S or not? Yes or no? Let's say I have if this circle here is a set S, okay, and I pick a point here. Can I find the ball that's entirely lying inside X or not? No, right? Okay, so that means I cannot include this boundary point here. Actually, I cannot include this boundary point. I cannot pick point from here. Otherwise, I cannot pick a ball. Okay. If I do this, then no matter how close to this boundary, okay, I can find an open ball around here. Okay. Just by considering the radius here. Okay. Okay. I want you to play around with these definition. Okay. It will be in your assignment. Next assignment. Okay. Okay, so all the closed set you can write it as a complement of an open set. Okay. Any question about this? So you need to know about what is open set. So to know about open set, you need to know about open disk. Okay, so the most important thing you know is about open disk first. Okay, and then use open disk to build open set. Use open set to build closed set. Okay, these three ideas. Okay, so open disk, use open disk to build open set. Use open set to build closed set. Okay. Any question on this definition? I put out the definition on the last lecture already. You can check out. Okay, it's in the last lecture. Okay, so equivalently, actually, there's an equivalent definition here. So this is a definition I give in class. So there's another definition given in the textbook. Okay, so this is given in textbook. This one is in class. And there's a definition in textbook. Okay, so what does textbook say? It says exactly what Zheng Kan said just now. So a set is closed in R2 if C contains all its boundary points. Okay. So it contains all its boundary point. Okay. So what's the obvious question you should ask here? Easing. What's the obvious question you should ask here? I simply tell you a statement here. Something is closed if something contains boundary point. What's the obvious question you should ask here? What's the obvious question you should ask here? Any question you want to ask? Huh? Yeah? 讲什么? Huh? What do you mean? What's the obvious question you should ask here when I tell you this definition? I tell you something is closed if it contains you know, right? So meaning the boundary point is in there. Then what is the thing that you don't know now? Huh? How do you show something is closed? Huh? Define something there. Find one thing. Huh? But this, no. Huh? Is there any word that you don't understand inside the second definition here? Huh? Boundary point. You should ask what is boundary point. I have pushed all the definition to boundary point now. So you should ask what is boundary point. Otherwise, how do you show? Right? I don't know close. Okay, I tell you what is close. And I say close if C contains all the boundary point. Then you want to show C is contain all the boundary point. Then what is boundary point? If you don't know boundary point, then how do you show it contains boundary point? You get what I mean? So this means what? So we need definition for every term. Okay. So we need the definition until we can have something to work explicitly. Okay. So I need to give you what's the definition of the boundary point. Okay. Here, a boundary point of C, first of all, is what? Is an element. Okay. Element AB in C. Okay. Such that what? Such that for every disk, okay, you make around this AB, okay, this disk, such that this with this disk, with the disk contain in C and points not in C. Okay, so this is something you can check already. This is something you can check whether it's true or false, this statement. Okay, so every disk you make, okay, at this point, it contains points in C and points not in C. This is called a boundary point. Does it make sense or not? What is boundary? Huh? Have you been to other country or not? Have you been to Singapore or not? Have you been to Thailand or not? Do you pass by custom or not? So when you are before the custom, you are in Malaysia. After the custom, you are in Singapore. So every ball you make around the boundary, it contains point in C and not in C. So you cross a little bit the boundary, you are in Singapore already. Before the boundary, you are still in Malaysia. Okay or not? So this is called boundary point. So how is it a boundary point? You make any circle around you, okay, you step a little bit away, you are in Singapore. Okay, step a little bit inside, you are in Malaysia. Not in C and in C. Okay, If you step up, it is noisy. Step inside, it is easy. Right? This is boundary point. Okay now. So then this one you can check already. If it contains all its boundary point, you need to check that. If all the points satisfy this condition here, is it in your set? Okay, do you contain all of them? Okay. For example, just now, right? The point I throw away is exactly the boundary point. Okay, because S is define everything inside the circle. Okay. So if you stand at the boundary point, make a circle. Okay. It contains point not in X and in X. No matter how small you make it. Does it make sense? Okay, no matter how small you make it. So these two are equivalence definition. Yeah, these two are equivalent definition. So this definition here actually generalized from where? Where's the first place you see close? Huh? Where's the first place you see close? Any first place you see the word close? Close interval. What is close interval? For example, what kind of close interval you have? 0, 1. Okay, this is a closed interval. So you have a line, real line, okay, and then you take all the point between 0 and 1 inclusively. Okay, you take all this point. Okay, no. So from here, right, from here, this interval here, which point is the boundary point? Which point is the boundary point of this interval? 0? 0.5. Okay, let's do 0.5. Where is 0.5? 0.5 is here, in the middle here, right? Okay. So if I make any ball here, does it include any point not in the interval and inside the interval? Does it include both these points? No, right? Within this ball, this open interval here, all the point is in the set. There's no point outside the set. So which point have this property that if you build any ball here around it, you will get point outside and inside the set? Which point? 0 and 1, right? So if you pick 0 and 1, okay, if you pick 0 and 1, no matter what open interval you make here, because ball go down a dimension become interval. So no matter how small you make it, right, you will still get point outside the closed interval and inside the closed interval. So 0 and 1 is the 0 and 1 are the boundary point of the closed interval stronger. Okay? Okay. So if I throw away these two, then this interval just become the open interval. So open interval is really the closed interval throwing out all the boundary points. And that's why we call open interval. Okay. So if I throw it out, I will get the open interval. Okay. Open interval. Open interval is what? Is equals to 0, 1, throw away what? Throw away 0 and 1. Okay. 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 But just now we also said that this closed set here is the whole set take out the some open complement, right? Complement of some open set. So what is so what is the open set such that 0, 1 equals to R throw away S? So what's the S I can take here? What's the open set I can take? Such that the closed interval 0 to 1 is equals to R throw away S. So this is the another definition of 0, 1 being closed, right? So we have two definitions, right? One of them is it includes all the boundary points. The other one is you can write it as a complement of a closed set. So what's the complement of an open set? So what's the open set you can choose here? What is the open set you can choose here such that this closed interval is equal to the real line taking out? Yes. Right. So I want to take x equals to what? So you have a whole real line, right? And then you take away 0, 1. What you left with? What do you left with? 0, inclusively or exclusively? So exclusively and then union with 1 to infinity. So is this thing open or not? Is this open? Open, right? Okay, because no matter what point you take inside here, you still can make small open interval inside these two intervals, each of these two. Okay, so take x which is open. Okay, open in the sense of open this. But this, when you go to real number, it decreases by dimension. So you talk about open interval. Does it make sense? Make sense or not? Okay. Okay. Another thing we want to talk about is boundedness. So let's talk about boundedness. So let's formulate boundedness. Okay, let's formulate boundedness together. So what do you think a set P in R2 is bounded? Huh? What do you think? If I have a set P is bounded, what do you think? How is a set bounded? So let's say you have a R2 here. Okay, how is the set is bounded? How do you think? How do you think of a set is bounded? And you have a flat plane here. So what kind of set is bounded? 什么是 bounded 啊？是有边际的 ，right？ 不是无边无际的。Okay, so how do you describe this in maths? 这个 wow, you are a bit advanced in this. So what I think about how I think about, so you want to bound it in a circle, right? Okay. So how about follow your path first? So this is actually what introduced in textbook. So this is actually what introduced in textbook. So a set P in R2 is bounded if there's this xy in P. Sorry, for all xy in P, there's this open this D such that all the point is inside the P. Okay, so meaning I have some set called P. Okay, I can bound it using some. I can bound it using some open this. Then I can use a circle of this to bound it. Okay, but what I think is I can control all the coordinate. I can control all my x and y. Okay, what do I mean by control my x and y here? So I can use 4 numbers to bound them. Okay, there's this M, N. Okay, capital M, little m, capital N, and little n. Okay, such that I can bound my x coordinate using above and below using little m and big M respectively. Similarly for my y, I can do this. All the coordinate is bounded by some number. So what is exactly I'm doing here? I don't use circle to bound my set. I use rectangle. So here I should draw it for you here. What's my bound here? So I should have something like M. Okay, let me draw like this. Okay, my M for my coordinate X. Okay, and then I have N, small n and big N, for example. So all my point is lying inside this circle here, rectangle. Okay, rectangle. Of course, depend on the negativity of my N and M, right? So my N maybe can go negative. My M also can go negative. Depend. Okay. So in this case here, we have N, M is greater than 0. But no matter it's negative or positive, you will get a rectangle. Okay, so you can either bound this set using a rectangle or bound this set as a circle. But these two are equivalents. Equivalent definition means what? If I can bound with a square, I can also bound with a circle. If I can bound the set with a circle, I can bound with a rectangle. Okay, does that make sense? So these two definitions are equivalent. Okay, so how to show some two segment are equivalent in discrete math? How to show two segment are equivalent? Are you guys being told? If and only if. Okay, so if you can bound by the square rectangle, then you can bound by a open this. If you can bound by an open this, you can bound by a rectangle. Is this true or not? Is this true or not? How should you construct this? Huh? If you have a set, okay, P. If you can bound by the circle, this can you bound by a rectangle? How? Let me. You just draw a rectangle portion. Okay. So you can try and use the measurement from your this to make your rectangle. Okay, you can use the measurement of your this with your rectangle. But how about if I can bound my set P using a rectangle, cannot bound using a this or not? How? 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 Yeah. You just make a circle that inscribe this rectangle here. Okay, but mathematically, how you write it out? How if I given you this rectangle here, how you construct this circle? What is the radius you should take? What is the radius you should take? Okay, what's the radius you should take? And then it depends on where this circle, this square is, right? This square maybe lie outside the origin. So what kind of length you want to take? Okay, so this become a question when you want to prove it. Okay, I will write it out in the lecture notes. You can have a read, and then if you have question, we will look into the notes next lecture. Okay, but the idea is like this: if you have a square, you can make a circle. If you have a circle, you can make a square. Okay. The first one is easy because I make my open this around origin, so it's easy to get this length you like. But when I talk about this square here can be everything, anything, any places in my R2. So this makes a little bit hard to make a circle. So let's say this square here is living here. Okay, what kind of circle I can draw? You can draw the small one, but you can also draw a bigger one. Yeah, this become tricky when you want try to write out proof. And then this is where the places where this proof get interesting. Whether you want to reduce the size of your this or not, or you just care about there's a this enough. I just make a large this for you, that's all. It's still bounded, right? There's this or open this, that's all. Okay, no matter how big or how small then this. Okay. So this make proof very creative. Okay. You can write it on your own way. Depend on your thinking and what you care. Okay, you write it out. Okay. Does it make sense? Make sense or not? Okay. Okay. So please understand the proof I will provide in the lecture notes. And then we will have similar question in the assignment. Okay. So we have introduced well motivated by this definition already. So let's sorry, let's appreciate this theorem here. Okay. So if you have a continuous function on closed and bounded set, then f attain both absolute maximum and absolute minimum. Okay, I know that something is a maximum or minimum. Okay, but how to find? Okay, how to find those things? Okay, how to find it? This become a problem. Okay, so they create another theorem. Okay, it says that if the thing you find, okay, is an abstract value, then the domain, the input value must be a critical point. Okay, so abstract value theorem just tell you an existence that is. I don't tell you how to find it. That's one. Okay, but this critical points theorem tells you how you find it. If the thing you want to find, okay, is an absolute value, then the input domain is a critical point. Okay. Now you should also ask an obvious question. What is the question you should ask? What is the critical point? Correct? I push. Yeah, correct, right? I push the problem from absolute value, extreme value to a critical point. Then you should ask me how to find the critical point now. Okay, so what are critical points? So there are three types of critical point here. Okay, so one is the boundary point, like just now I talked about the one variable case. It's on the boundary point. Okay, or the point, it is stationary point. What's the stationary point? Okay, first of all, it's an interior point, okay, such that the gradient of P0 is 0. This is the same as the one variable case where the first derivative equal to 0, right? Stationary point. First derivative equals 0, and then you check second derivative whether greater or 0, whether it's 0 or less than 0, and then determine maximum minimum. This is the same. Okay, stationary. But now you go up one dimension, so we need a gradient here. Okay, gradient is 0. I didn't tell you what is interior point. What's interior point? It's just a set. It's just a set. Take out the boundary point. What's left is the interior point. Okay. Yeah. Okay. No. Complement of boundary point. And then the other point is called a singular point. Okay. So this is a point where f is not differentiable. Because if it is not differentiable, how you get the gradient? Cannot get. Okay. So you can only straight away check on that point what is the value, and then compare with the rest. Okay. If you cannot get the gradient, because stationary point you need the gradient. But if it is not differentiable, you cannot get the gradient. So we call it a singular point. Okay. So basically you are boundary point, stationary point, and singular point. Okay. So these 3 points here. Okay. You need to check this point. So what's the procedure here? So to find an absolute maximum or minimum values of a continuous function on a closed bounded set, what you need to do? You need to check values on stationary points, check value on singular point. Okay, just these you just sub value in. And then you find the abstract values f on the boundary as well. Okay, compare all these. Which one is the largest? Then this is the absolute maximum value. The smallest one is absolute minimum. Okay, let's try the example of this. So find absolute maximum and minimum value of the function x squared minus 2xy plus 2y on the rectangle. So you are given a rectangle domain here. So S is bounded by 0 to 3 and Y is bounded by 0 to 2. Okay, so you can draw this rectangle out. So this is not graph yet. This is just a domain. Okay, the graph is living in R3. Okay, so there's some plane here. Okay, you look at the plane on the top, at the top of this rectangle. Okay, and then we try to find maximum minimum value. Okay, so what's the first thing we can do here? Okay, so the so the obvious thing you can do is to find the stationary point. And let's do stationary point here first. It's the same in the calculus of one variable, where you find first derivative, the point where first derivative go to 0. So let's find stationary point first. Okay, how to find stationary point here? We need the gradient to equal to 0. So how to find the gradient? And Roshan, can you give us the answer? What is the gradient of this f? What is fx and fy? F with respect to x and f with respect to y. So just take first derivative of this surface here. Can you differentiate? Can you partially differentiate this function f with respect to s? To x, correct? Minus 2y, and then comma, is it? Comma, minus 2x, and then plus 2. Good. Okay. So to find stationary point, we need to make this a 0 vector. Okay. So we need to set this gradient as 0 vector. Okay. So what do you get? 2x minus 2y equals to 0, and minus 2x plus 2 equals to 0. So together, solve this system of linear equation. What you want to do? Okay, I don't think you want to do row reduction. Okay, so you just simply solve it. So x equals to 1 from the second equation. Correct. Okay, and then you sub it into the first one, where you just get y also equals to 1. Can do row reduction, I see. Finish LM, forgot already. Okay, never mind. So solve this using a system of linear equation. Okay, solve it. So you get what? So this is just s and y, right? So our point is on the surface. Okay, it's on the surface. So these 2 points here will give us f11 equals to 1. Okay, so you are on the x equals to 1, y equals to 1 at the height 1. Okay, so this is our stationary point. And then what else? We need, let's do singular point. Any singular point or not? Any singular point where this function is not differentiable? This function is what? It's just polynomial. Okay, polynomial is always differentiable. So there's no singular point. Okay, so there's no singular point here. So singular point doesn't exist. Okay, because polynomial are differentiable. Okay, then finally we need to check the boundary point. Okay, we need to check the boundary points. Okay, So what's the boundary here? What's the boundary here? Just now say what? What are the boundary? If I stand on the boundary, I must have point. If I make a circle around me, I must have point in the set and not in the set. Okay, so where is the boundary point for this rectangle here? And what's the boundary? All the four sides. All the four sides, right? So these are the boundary. Because no matter what circle you make around here, you will have point outside and inside. Okay. Alright. Okay. Okay, so there are four boundaries here. Namely, they already named for you already. L1, L2, L3, and L4. Okay, so these are the four places you need to check. Okay. So how about we keep this for next time? Okay, because it's 250 almost. Okay. You can try along this boundary, find the smallest and largest, and then compare to the rest. Okay, which one is the absolute maximum or the absolute minimum? Okay. Try and check along L1, L2, L3, L4, which one is maximum, which one is smallest. Okay. And we will continue on the next lecture.
Hello.
So Roshan, please return me your exam, okay? If you have any question about it, you can ask. And any one of you want to ask about your project, also you can approach me. We will move up. Okay, let's move on because someone will be taking this class. OK 啊，只是为什么你没有 intro 还没有写啊？
加了啦啊。
哦，我还没有看，你后来。